what's the probability of all the joints and all the distributions in the world that she walks into mine? And in this question, we're going to talk about quantifying how data changes together. Now, we're not quite at the point where we're talking about predicting things, but this is a small and critical building block. I want to remind you of one of our summary statistics, our summary statistic called the variance. And when we computed the variance, we said this is a measure of how the individual data points are distant from the mean. We compute it by taking each individual data point, subtracting the mean, and then squaring that and finding the average distance that they have, the average square distance they have with the mean. We call that the variance, and it was one of our statistics that gave us a sense for how spread out this distribution was. And we said the units for this weren't that great. They're squared units, so maybe instead of using the variance in terms of talking to people about where that distribution is, or where the values in that distribution lie, we might talk about things like the standard deviation, but for the most part, we have a good sense, a good bead on that variance. Well, what if I have 4 different data sets? And I'm going to take 2 of these data sets, and what if I compute the difference from the mean of one data set and the difference from the mean of the other data set, and I multiply them? If you think about this, what will happen is, when one of the data sets is very far away from the mean, if the other data set is also very far away from the mean, you'll get a very large value. If one of the data sets is very close to the mean and the other data set is very close to the mean, and you multiply them, you'll get a very small value. And when you take the average of that, you'll get some value that indicates how they move together. This metric here is called the covariance. And so if I compute this, I'll get a value, 0.1544, and that's my value that I'm referring to as the covariance. Now I can compute this directly using NumPy, and you can see I get the exact same value, but I want to talk a little bit about what this is. And I want to point out something that you have almost certainly spotted. When I compute this covariance, you can see I give it a DDOF parameter, and we've seen these come up before when we did things like standard deviations and variances. The covariance is a sample statistic. It does have to make certain assumptions about what the population looks like versus what the sample looks like, just like there was that distinction between the sample variance and the population variance, and there was that Bessel's correction. For covariance, you can think, if you're looking at these values, you're still making some assumptions about what the population looks like from a sample. You also have to take into account that you might need to apply some sort of Bessel correction, like degree of freedom based correction on this. And in fact, we can even see that, the Bessel's correction factor looked something like this. And you can think that if we were to compute this mean and then multiply times the factor, we'll get what NumPy's covariance gives us if we give it the default degrees of freedom of 1. And so one important thing to bear in mind is we are not moving away from this idea of there is a population out there, but we cannot see the entirety of the population. We can only see what we've sampled. Now, setting that aside, let's talk a little bit about what this covariance really means and how it behaves. If I compute this covariance, it doesn't give me a single value. It gives me a matrix. And this matrix corresponds to the covariance of data 0 against data 0, data 0 against data 1, data 1 against data 0, and data 1 against data 1. Well, one thing that you can think about is that reverse diagonal is always going to be the same value, because if you look at the formulation here, it doesn't matter if you compute data 0 minus data 0 mean times data 1 minus data 1 mean, or if you do that vice versa, it doesn't make a difference. And so that diagonal going this way, it's always going to be the same thing. The other thing I want to draw your attention to is this formulation is really just, taking all the different ways we can mix and match data 0 and data 1 and data 0 and data 1 and computing this. If we take 4 data sets and we compute the covariance of them, it'll look something like this. And you can see we now have how does data 0 and data 1 change with each other, how do data 1 and data 2 change with each other, and vice versa. And you can see that reverse diagonal is, in this case, it's not quite the reverse diagonal since we're not matching up exactly the same thing against the same thing, but you can see we have these strides or these diagonals here where everything is the same. But one important thing that you'll notice is the diagonal going from the top left to the bottom right. Those values are what happens when we take something and we demean it, and we multiply it times something else that's demeaned, and we compute the mean. If we're doing that against the same data set, if we're taking the covariance of a data set with itself, it's just the variance. This is the relationship between the variance and the covariance The variance is merely something's covariance with itself. Now, we had some difficulty interpreting the variance, in part because the units are really weird. If these were physical measurements in feet and inches and meters, then the units of this would be meters squared or feet squared, which would be strange because we would be talking about maybe something like height, and then we'd say, oh, the variance is feet squared, which is an area metric. Doesn't quite make any sense, which is why we'd use something like the standard deviation. We take the square root. Well, in general, when we talk about covariance, what we're looking at is the tendency in a linear relationship, and we're largely focused on just the sign of this value. We're focused on if that sign is greater than 0, then that means that the large values of the left-hand side and the large values of the right-hand side move together. The small values of the left-hand side and the small values of the right-hand side move together. If that sign is less than 0, then they move in opposite directions. The large values correspond to the small values correspond to the large values. If it's 0, we can see there is no clear relationship, but critically, the magnitude of this covariance is very hard for us to interpret in any meaningful fashion. The only really way we can interpret this is maybe the magnitude of something's covariance with itself. That's just the variance, and we have used that before. But in general, a data set's covariance against another data set is difficult for us to interpret in terms of its magnitude, in part because you can think these values are not normalized. And because these values are not normalized, what does it mean if the value is 100 versus 200? That could be an artifact of the scaling of the values, the units of the values. If we computed the covariance in feet versus the covariance in meters, the values would be different. But it doesn't tell us anything they're different, but the sign would be the same. And so largely when we talk about the covariance, we're talking about that sign and getting a very, very basic sense of how things correspond to other things. Now there's a little bit of sleight of hand here. Previously, when we had looked at these data sets, I showed you a large population, and then I sampled from that population. And how I did that sampling didn't matter, and how those data were aligned didn't matter. When we talk about things like the covariance, we're matching things up. And so, if we're talking about data set 0 and data set 1, we're assuming that the positions within those data sets correspond in some fashion. It's the same entity against the other same entity. They're on some sort of time series, so it's the same time point against the other same time point, the same pandas index values, the same label against the other same label. We do have to have some consideration that these are matched up in some fashion, because otherwise you could think for these computations, the covariance, if I sort one of these, would change. But that doesn't really make any sense. And so there's an implicit understanding for all of this discussion about things like covariance and correlation that we're now looking at data sets where we have some implicit matching of these values with each other. And that's going to make a little bit more sense when we think about this in terms of just simple y-x two-dimensional graphs, because there is that matching. You have a corresponding x value and a y value that gives you a particular point on a line. But do keep that in mind, because that is a little bit of a sleight of hand. But probably the most important question out of all of the questions that we'll ask is, why do we care in the first place? Our goal is to make predictions. Our goal is to try and figure out what's going to happen in the future. How does covariance help us? Consider this. If we discover that there is a clear covariance linear relationship between two pieces of data, that does not tell us that there is a causal relationship between these two pieces of data. It does tell us that there is clearly an observed relationship, and if we take that relationship that we observe and we use good judgment and maybe some additional statistical approaches, we can say, well, yeah, there's a reason, right? Happiness correlates to, how many days off per year you get. It makes sense. There's a clear causal relationship there. There would be a clearly demonstrated covariance there, and we care because if we know one of those two inputs, we can use that to guess something about the other. If we don't know how happy you are, but we know how many days off you get, maybe we can guess how happy you are. And so covariance starts to give us that beginning idea of, can we have some data set that we can see, and we can find a relationship with some other data set we can't see, and use the thing we can see to guess about the thing we can't see. Now, we can't do it too effectively with covariance, but it's the beginning of the idea.